Okay, in this video we'll do the conclusion of section 11.3, which is the dot product. So we're going to start with talking about resolving a vector b into vectors parallel to two other vectors. So let vector a and c, and your textbook doesn't use c, it uses a prime, but I don't want to confuse our a and a prime, so I'm just going to use c. Let vectors a and c be perpendicular, and the vector b be in the same plane as A and C. So remember, we can move vectors anywhere, and we looked at a little visualization I did a couple of lessons ago where I took two vectors, I moved them so that where their initial points touch one another, and those two vectors made a plane. So it doesn't matter where A and C are, we can take them and put their initial points adjacent to one another and make a plane out of that. So, and then B has to be somewhere in that plane. Now, if this is the case, then we can write B in terms of vectors parallel to A and C. This is called resolving B into vectors parallel to A and C. And basically what we're doing here is kind of similar to how we use the vectors I, J, and K. Those three vectors are all perpendicular to one another, so we can write a vector, some vectors in the xy plane, and we write those vectors in terms of vectors parallel to I and J. That's what we're doing, and the reason we can do that is because I and J are perpendicular. So now it doesn't matter what the two vectors are. They don't have to be I and J. We can take any two perpendicular vectors, and if there's another vector that's in that plane, we can write that new vector in terms of vectors that are parallel to these two vectors that we started with, as long as those two vectors we started with were perpendicular to one another. Sorry, this shouldn't be a period right here, so let's get rid of that. And is given by B equals the projection of B onto A plus the projection of B onto C, where so this formula always holds, and we'll be given the vector B and the vector A and the vector C. So we're already given that. We know how to compute that from our last portion of this section. We know how to compute this. But because this formula always holds, we don't need to compute all three of them. We have that. Once we compute this, then we can just use algebra on this formula to find that. So the way that we'll compute this is by just subtracting this from both sides. So where the projection of, actually, let me put this over here, where the projection of B onto C is just equal to B minus the projection of B onto A. So this just saves us a little time in computation by using this. So we want to rewrite B in terms of this vector plus that vector. So we need to find that vector and find that vector. So we'll do an example from you all's textbook where we use this formula. So we're going to look at page 128, number 16. Page 728, excuse me. Number 16, which says in exercises 15 through 17, A prime, which is going to be C for us, so I'm not going to use A prime. So A, C, and B lie in the same plane. Show that A and C are perpendicular and resolve B into vectors parallel to A and C. So they give us three vectors. A is the vector 1, 1, negative 1. What they call A prime, but we're going to call it C instead, is the vector 2, negative 3, negative 1. And the vector B is 0, negative 5, 1. 0, negative 5, 1. So the first things we're supposed to do is check that A and C are perpendicular, but for sake of time, I'll let you all do that. You take the dot product and ensure it's 0. Remember, this process only works if those two vectors are perpendicular. So if you were just told to attempt this process, you need to first check to make sure that those are perpendicular in the first place. But it's a rarity that you would have to do that, because you would also need to know that B is in the same plane as A and C. So a problem like this, you'll be given vectors that are going to work out nicely, because we wouldn't have a way of checking just yet that B is in the same plane as those two vectors. All right, so now what we're going to do is I'll let you all do the dot product on your own. We're going to go ahead and start this process to try to write B in this way. So we are just rewriting a vector that we already have. So at the end, I'm going to skip simplification. Otherwise, we'll end up right back where we started. So I'm going to start by computing this. So we want the projection of B onto A. So in order to do that, we need to have to do A dot B, which is going to give us 0, then minus 5, and then minus 1. So we get negative 6, and then that over the magnitude of A squared. And the magnitude of A is the square root of 1 plus 1 plus 1. So we get the square root of 3, and then we square that, which gives us 3. All right, so these are formulas that we discussed in the last lesson, or the last video. Then times this vector A, the vector that's at the bottom down there. So 1, 1, negative 1. Now, other than changing this to negative 2, I would normally leave this exactly like that. But because now we need to find the projection of B onto C, I'm going to simplify this so we can plug it into this formula. So we already have this part. Now we need this part, and we're going to use this formula to find it. So let's just simplify this. This is negative 2 times this, which gives us negative 2, negative 2, and then positive 2. So now the way that we find the projection of B onto C, we could use this same process that we use here, but we don't need to. It's faster to use this instead. So we take our B, which is 0, negative 5, 1, and then we just subtract from that what we found here, which was negative 2, negative 2, 2. So notice the subtraction is much easier than doing a dot product and a magnitude and all that good stuff. So we have 0 plus 2, which gives us 2. And then we have negative 5 plus 2, which gives us negative 3. And then we have 1 minus 2, which gives us negative 1. So notice these two vectors by definition should be just multiples of the vectors A and the vector C. Let's check, is this vector that we get here a multiple of A? Negative 2, negative 2, negative 2. Yes, all we did is take this vector. I mean, you can clearly see that right here, that it's negative 2 times that vector A. Down here, is this a multiple of B? or of C, excuse me, of C. This is a multiple of C. It's just C times 1. All right, so now we put our answer together. You don't want to simplify your answer here, because if you simplify, you'll end up right where you started. So we want to just rewrite B as this plus this down here. Or I'm actually going to, so we see the actual vectors. This is -2 times 1, 1, -1, which is what we have right there. And then plus 1 times 2, -3, -1. And I put these out here just so that we can see that what we actually have is B is just -2 times the vector A plus 1 times the vector C. So now it's kind of like we've rewritten B in that IJK form or IJ form in this scenario, but we just use A and C instead. All right, so that's how you resolve a vector into vectors parallel to given perpendicular vectors. All right, now the last topic in this section to cover is work. So the amount of work done by a force, which we'll call the vector capital F, in moving an object from a point P to a point Q is, and actually let me specify something else, along a straight line, because we're going to calculate work a little bit later in the semester where we're not going along a straight line. Is W, which for work, equals F dotted with the vector from P to Q. Now we know how to compute a dot product, but we also, in just the basic way by definition, we also know that's the same as the magnitude of F times the magnitudes of PQ. I'm going to squeeze the vector PQ, then times cosine of theta, where theta is between 0 and pi, is, I'll let you all finish that, is the angle between the vectors F and the vectors PQ. All right, so I'm going to quickly run through an example just because we're running out of time for this particular section. So we're going to quickly go through number 34 in your textbook. So page 729, number 34. So go over this again on your own because I'm going to go through it so fast. So a person exerts a horizontal force of 20 pounds on a box and pushes it up a ramp that is 15 feet long and inclined at an angle of pi over 6. How much work is done on the box? All right, so I'm going to sketch a little picture of what's going on here. So we have our ramp, and this angle right here they told us is pi/6. And they told us that the length of the ramp, so let's make a little, like that there. So that's our horizontal. The length of the ramp, they said, is 15 feet. So that length right there is 15 feet. And there's a box on the ramp. It's getting pushed up the ramp by a horizontal force. So the box is not pushing at an angle. It's not being pushed. The force is not coming at an angle this way. The force is coming in the horizontal direction. And they told us that that force is a force of 20 pounds. We're just going to call that F. So now the amount of work being done is, if we knew what F was, if we knew the actual, and we knew what PQ was, so where this is P and this is Q, then we would do the dot product that way. But we don't know what P is, nor do we know what Q is. We just know what this distance is. So it's easier for us to just use the magnitude of F times the magnitude of PQ times cosine of theta, because they gave us our theta. And we know what the magnitude of F is. They told us it's a 20-pound force. So its magnitude is 20. And the distance between P and Q, which is the same as the magnitude of the vector PQ, they told us is 15 feet. So that's 15. And then times cosine of our angle, which was pi/6, if I'm not mistaken. Yes, it was pi/6. All right, and you would just simplify that to get the amount of work done and the amount of work that force is doing to move that box that 15 feet. All right, so that is the conclusion of section 11.3, and we will start 11.4 in the next video.